giving up something outside of the log to gain something inside of the log, that's always a losing proposition, or at best, kind of even at the very lowest NR. So what's the interest in frequency?
No, so in the decentralized setting is what I'm mentioning. This,
but I'm saying the best you can achieve is reuse 1. So why the interest on fractional frequency reuse?
I'm not sure if I understand what's frequency reuse.
Okay, I think what you're implying by no frequency reuse is that there is no fractional frequency reuse.
Fractional frequency. Yeah.
So in fractional frequency reuse, you split the band, say,
right,
and you create orthogonal channels. But the cost of doing that is an out of the log, because the throughput is B log 2 of 1 plus SNR.
Right.
B is outside.
Yeah,
so you would cut the B in half for some improvement of inside of the log is INR.
Right.
That's always a losing proposition.
Okay.
And I guess another point isn't the taking turns and kind of backing off. And I mean, you end up having sharing in time. Does it really make a difference if you share in time or in frequency?
And you always lose as well, because that's an orthogonal out of it. So if you share in time, you will do 1 over T on the outside. Well, not always. If the rho SNR is very high and the SINR is very low, you may end up winning by separating in time or frequency. But those are low probability events.
I don't think it's looking at capacity. I think it says I have a lot of bandwidth and I have some requirement.
Okay.
Yeah. Maybe the example, once I show how the mechanism works, perhaps I'll be able to answer that. So in a game theoretic, just mentioning what I did read for as part of literature survey was that it assumes an additional overhead about the knowledge of other existing users and their use subcarrier usage within the network. So the bottom line is optimal resource allocation in a decentralized competitive environment, at the same time ensuring fairness and some spectrum etiquette is not straightforward. So the network model that I assumed in my simulation, and some of the key assumptions was that I consider a static cognitive radio network with directional single hop links. Links are created randomly with some fixed bandwidth demand that I decide. All the links should share a common spectrum, and we propose to use non-contiguous OFDM with fractional frequency to use to share the spectrum. So when I started looking for such algorithms, I bumped across one of the algorithms that prevail in TCP, and I thought I could use some analogy to build this algorithm in decentralized radio frequency, decentralized fractional frequency reuse scheme. So what I want to mention here is the TCP has a congestion control algorithm called AIMD, and the TCP congestion could be thought of as the Cochannel interference in the scheme, and the contention window that it maintains could be thought of as the number of OFDM subcarriers used by the link. So in addition, if you do a careful subcarrier assignment, and what I mean by that will be clear in a couple of slides, it will enhance the frequency reuse globally. So TCP, as I mentioned, TCP uses this AIMD-based congestion control algorithm and maintains a contention window sized R. Each source in TCP maintains, and it increments or decrements, increments in an additive fashion with a increment size of alpha when there is no congestion, and when it faces congestion, it reduces multiplicative by a factor beta. So it's essentially trying to probe into the network for more capacity by incrementally increasing and backing off if the network reacts with some congestion. So some of the convergence behaviors of this communication network, AIMD-based communication network, was analyzed by Worth and Stankiewicz, and some of the stability properties are also explained in the other reference that I mentioned. So I would now explain the simulation setup and the network topology that is used. So consider a 3-link case where we are at link 1 currently, and there are 2 interfering links 2 and 3, and we want to place this network topology geographically. So we denote P12 as the relative distance between link 1 and 2. What I mean by it is normalized with respect to the link 1's distance between the transmitter and receiver, and so as link the distance P13. So and it's also assumed that the interfering links are symmetric in nature, which means P12 is same as P21. It's just an assumption that I have in the scheme, and also it's normalized with unit distance. The distance between transmitter and receiver on a single link is set to 1. So with this setting, we randomly populate a distance table where it's populated for a 6-link network where it's basically showing, for example, the first row, link 1 interferes with 2, 3, 4, 5, and 6, and they are placed at the distances as shown, and so on and so forth. The infinity basically means that, for example, link 3 and 4, they do not interfere. They're spatially separated by a large distance, and they can completely reuse all the subcarriers in question.
So the numbers are incredibly close to each other. With the propagation the way it is, if you double, quadruple the distance, and you had a distance to the 4th power, you get 16 times or more the attenuation.
Yes, but I just wanted to know since the algorithm is new, I just wanted to know the behavior, and I didn't really take realistic distance assumptions. It's just an arbitrary value for now.
Fair enough.
But we can play around with realistic distances. The way I populated this distance is I took an orbit number 5 and then spread with some standard deviation. So that's how it's populated this. And once we have this distance table, we can quickly calculate an interference table, just as you mentioned, with an inverse square law, path loss exponent of 2, and we get what we call as the link gain between any 2 interfering links. So the spectrum allocation and deallocation scheme here is broadly split into 2 steps. The AIMD algorithm basically puts the rate by assigning the number of subcarriers, and then the subcarrier assignment and deassignment, which I mentioned, should be done carefully, which I'll explain in the next slide, assigns the actual subcarriers corresponding to whatever number was decided. And this split approach basically we believe ensures fairness during this rate allocation procedure and efficient spectrum utilization during the subcarrier assignment phase. So quickly mentioning the system variables, I stands for the link index, and DI is the number of subcarriers demanded per link, and RI is the number of allocated subcarriers after the AIMD decision is made, and N, capital N, uppercase N, denotes the total number of subcarriers in the whole network available. And this N is common for all links. This is the commonly available spectrum, and we assume a fixed subcarrier spacing, and therefore the FFT size is common for all. And the algorithm stops for a link I when it reaches its preset demand, EF.
So RI
is
equals DI is when you stop? Is that what you mean?
Yeah, so RI keeps incrementing additively, and it continues to increment till it reaches DI, and DI is set, predetermined.
So that's sort of like, if you have more time, maybe you can spend a lot of time working on the ABC project. Is the demand the number of carriers, or is the demand really your rate?
So now, for now, the resource here is just the subcarriers. I'm not even considering waiting power. I'm just considering constant power. Just strictly speaking, in terms of subcarriers, let's go ahead and see how it.
So when you say constant power, you mean constant power per subcarrier. Like if you transmit on one subcarrier, if you add a subcarrier, you actually double your transmit power.
Yes.
Also because of the modulation.
No, I'm sorry.
So quickly defining what co-channel interference here means, when two or more links use the same set of subcarriers, they would interfere and the carrier to interference ratio will decrease for all those interfering links. And we use this metric CIR for each link by calculating, and it is calculated by counting how many subcarriers are common between any pair of, any pair of links I and j, and j will go for all the number of interfering links in my case, in this case, and will be scaled by the link gain between I and j. So in other words, mathematically it's just the dot product, the k vector, which is the number of interfering links for the link I in consideration, and the link gain with respect to I and all the interfering links. So we also set a threshold, for now arbitrarily, and decide whether to do additive increase or multiplicative decrease based on the current running carrier to interference ratio for that link. So this equation is exactly similar to the AIMD's congestion control equation, where the contention window is now replaced by Ri, which is now denoted by the number of subcarriers, and N is the time index.
So
Yes.
is K a matrix?
No, it's it's one by, it's single, it's a row. So
It's a row vector.
row.
He should really describe his scheme. I think the way he envisions the scheme is at a certain point everybody checks available carriers for his link. And based on that, for each link, K is the number of common subcarriers between I and J links.
I think, okay.
That's
I
where
was
they
thinking
interfere.
I was planning to explain that in the next.
Maybe you should keep going along.
So during allocation, when we decided Ri is some number after some number, so the way, okay, so let me, so each node independently, in a realistic scenario, each node works independent of each other, and they keep incrementing their subcarriers by observing the spectrum. So it is assumed that each node has a co-located spectrum sensor. It takes a snapshot of what is the local availability of spectrum, and then from the available white space, it will assign one subcarrier at a time, and it will continue to do so until its carrier to interference ratio reaches a set threshold.
But the measurement the collocated spectrum sensing device will make is very likely to be uncorrelated with the interference that transmission will cause, since that receiver is likely to be several coherence distances away. So it is, as we know, what's the benefit of having uncorrelated measurements?
So here, for now, I have assumed that these distances P12, P13 are relatively large. I mean, here relatively is not too large, but what I'm saying is,
But it's something longer than the correlation length, which is just a few wavelengths, right?
so I don't think I understand.
Okay, so
you,
I'm trying to communicate with you,
right.
but by necessity I make spectrum sensing here. That information is uncorrelated with the noise characteristics of the receiver,
right?
since we're many wavelengths apart.
Right.
So if the uncorrelated measurement is just as bad as no measurement at all, or just as good as no measurement at all, right?
Yeah, I understood your question now. So when I said local spectrum availability, it is after a link rendezvous procedure, which I'll explain later. They agree on a commonly available spectrum set.
Over some other channel?
Yeah, it's an out of
Why didn't
band.
they pass the information over that other channel?
I'm sorry?
Why they not pass the traffic over that channel if you assume it's already there?
It's assumed that in future work it will be a narrowband channel within the same data set, but for now the signaling mechanism requires a lot of development, and for now, just to simplify things, we kept it as out of band to see how the, so you're right, that scheme is still futuristic.
Just for the record, I point that the whole thing of cognitive is a little bit less compelling when we assume that the genie is telling everybody what's available or not available. Which is the equivalent of assuming that you have a control channel that all this information can be exchanged. Right?
So so the background of his job, right? He has worked on the NEC in parallel with this work, and it's been a game theoretic environment. Okay.
We're not competing with NEC?
We're not competing his thesis contribution. And in terms of his work, his intention was to, if he had another year, or to put this setup in the test bed.
Right.
And for that, he actually had proceeded in building a random protocol together with there was some synergy between NEC project and this project in the sense that we did sensing.
Okay.
We used NC-OFDM. He's going to talk about that too. We used NC-OFDM, and we were trying to find which sensing carriers from both things which are available, how many monitors you have, and then there was always this question about, and we still have to sort of work out the question of common channel.
Yeah, okay.
So
realize
we initially started out with...
We scratched the surface, but it's a good one.
Yeah.
Okay, thank you.
Thank you. Okay, so going back to the allocation phase where the subcarriers will be selected randomly from a locally available spectrum, which I just explained, will be a commonly available spectrum between a transmitter and a receiver. And if pretty soon, when everybody independently increments this number of subcarriers, we will run out of free spectrum, and they would have to select from the entire range of the entire operating range, which is the commonly used size for the FFT in the NC-OFDM scheme. Now, during deallocation, however, when we have to deassign the subcarriers, so let's say beta is set to half, which means if I had 10 subcarriers right now, after deallocation I should be having only 5, and I have to knock out 5 subcarriers from my OFDM. So how do I do that? So while doing that, it's not random. It is random, but it has a bias towards the ones which are, so I go one subcarrier at a time and see how many links are using that subcarrier and knock out the ones which are being used by the most number of interfering links. So some of the metrics to compare our results are, I defined something called as a weighted sum utilization based on a signal to interference ratio for a link. And in my scenario, the signal to interference ratio normalized with respect to unit distance, since we assumed, is given by the ratio, the inverse of the total sum interference perceived on the link, in addition to the noise. And the normalized capacity for that link with respect to no interfering case is given by that. And what I'll be really looking at is the total sum utilization, which is simply the sum of all subcarriers. But I would also plot the weighted sum thing given by U.
So is that equation for this, the SIR kind of a shorthand? Like, what is that sum really over? Is it over an interference set? Like a set of the J's that are using the subcarrier? Or is it really J equals 1 to K?
So K is the number of interfering links for, let's say, I, in this case. So, gamma I. So that will keep changing. K will keep changing for every link.
For is K?
So K is from here. This link gain matrix. So K is 4 for link 1, and K is 3 for link 4. So there are 4 interfering links. 2, 3, 4. I'm sorry, 5. I'm sorry, 5. K is 5 for link 1 because there are so links 2, 3, 4, 5, and 6 all interfere with 1.
Okay. How about link 4?
So link 4 is having only 3 interferers.
So when you do that sum for link 4,
yeah,
the way you wrote it, you go J equals 1 to 4, but really it's J equals 1 to
okay, yeah. So you're going in sequence.
4, 5.
So it's the non-zero entries will be
Very different from
Yeah.
that.
I think it's not
so
very-
J belongs
I told you
to the
this, but
interfering set, right? Now, it's not J equals 1 to 4.
No, this is
It's
not
a sum
very-
over the interfering set.
That's why it's-
Yes.
Okay.
And we also, for fairness, we use the Gen fairness index, which is given by this, which is commonly used in TCP networks.
Shouldn't you get a different SIR for each subcarrier though? So you're link 4, and you use some of the subcarriers, not all of them.
For calculating the SIR.
And one of the 4 interferers, they
might be
some of the same subcarriers as you, but you know they should be. You count the interference only when the interferer uses the same subcarriers. You do this calculation for each subcarrier.
Per subcarrier, per interference.
Okay. All right. So you left out kind of the subcarrier index.
And yeah, that is a little less. Sorry for that. I should have fixed it. So, in simulations, we thought of 2 models here for backoff, depending on how they back off. One we call is an all backoff link, in which all backoff case where when a link decides to back off, all the interfering links in that local interference group should back off, and it's done together in simulation. But in practice, these backoffs would not happen at the same time because it will take some time for. There should be some practical considerations which are discussed later as to how to ensure that all the links in the same interference group back off in some fixed duration, and the details of that will be discussed. The other scheme is a probabilistic backoff scheme where only a subset of those links decide to back off based on a Bernoulli trial. And to ensure fairness, we think the probability of backing off should be set directly proportional to the link's cost average throughput. In other words, if a link has used a lot of, the link has had a pretty good throughput for a long time, then its chances of backing off is pretty high. It should be set that way to ensure. The key idea is when links back off, they will give up some tones to the links that decide not to back off. But this has not been. I would study only the all back off model and present results to now. So just to give you a snapshot of how the AIMD process looks, this shows the AIMD process for 6 links. The color represents the 6 links, and on the y-axis is the number of subcarriers they use. Each link can use is operating with a constant FFT size of 64, which means that's the maximum number of subcarriers theoretically possible. If there was only one link, it would go ahead and use all 64. And I'm just showing a small time fraction of 200 iterations just to show how the process behaves over time. In this graph, I've said basically alpha, the number of subcarriers to increment is 1 subcarrier at a time, and the rate by which they go to half, they decrease subcarriers is half. And in simulation, it's only 1 event per time instant. That is either allocation or deallocation based on an individual link's carrier interference ratio. So the green line is basically an exponential moving average with a window size of 100, just to show an average level of. So in this case, if it's not clear, the average total number of subcarriers used in the network is around a little over 80 subcarriers. And the bottom graph shows the sum rate that I explained in the previous slides, corresponding to the network scaled with the individual capacities, which differs for a signal interference ratio for each link.
What's the total number of carriers?
So the total number of subcarriers here is 64 for all the links. And it's also assumed that each link here has a fixed demand of hundreds of carriers to allocate. And therefore, you see that the AIMD process never stops. It keeps demanding more carriers. So with this setup, we thought we should vary the parameters alpha and beta to study how the sum utilization, average sum utilization behave. So on the left axis is where alpha is incremented to by a factor of 2, and beta is reduced by a factor of 2. So with this, we calculated what is the sum utilization for the same interfering set that we mentioned, and it was observed that there is an upward trend for the sum utilization. Now, then we also wanted to plot how the fairness behaves, and it turns out it behaves in the opposite way. It takes a downward trend with increasing alpha and decreasing beta. So, however, if you notice that the rate of increase for the rate of decrease, for fairness with respect to alpha is steeper as compared to beta, which is also evident in this case, although it's not very clear. So there's clearly a trade-off with some throughput and the fairness within the network. So as alpha goes up, the rate of increment, the rate of additive increase, and beta goes down, the sum throughput goes up, but at the cost of reduced fairness. The other experiment that I wanted to do is to see how this AMD process behaves with drastic changes in the network demand. So what I mean by network demand here is, in the previous plots, as I mentioned, the demand for each link was set uniformly to 100. And I changed the demand to a random set halfway through the simulation at about 500. And as you can see, the sum utilization remains pretty much at the same level, the average sum utilization, at about 80. However, the fairness momentarily goes down somewhere around 500, actually 400 in this case. And the third experiment that I did was just to show if now the interference matrix that I had shown before, each link had 4 or 5 interfering links. Now I wanted to see how the network, the algorithm will behave if I had only one interfering link. I also had the case where no interfering links are there, but it was way trivial. I didn't put the graph here. But in this case, as you can see, the sum utilization, average sum utilization is somewhere around 100 now, which was expected because it's a little, on each link the perceived interference is a little less. Some of the inferences that to draw from this simulation is that AMD law-based spectrum allocation is feasible, as we can see from the results. And one of the key trade-offs to mention is when alpha goes up and beta goes down, the average sum utilization of the network increases, but at the cost of reduced fairness. And we also showed that it's quite robust against any drastic change in the bandwidth demanded in the network and the interference perceived. And I went ahead and tried to implement this on the GNU Radio platform. And the overall flowchart for this frequency assignment, subcarrier assignment, AMD-based subcarrier assignment would be something like this. Instead of the carrier to interference ratio as the metric, here I decide to use the packet error rate at the receiver. So I fix the packet error rate threshold and I decide whether to do an additive increase or multiplicative increase. So with this implementation in mind, since I was involved in the NEC project and we had a problem at hand to develop and evaluate experimentally a dynamic spectrum access scheme, me and Samson worked towards developing some of the dynamic spectrum access schemes in the orbit environment using GNU Radio. So the techniques of DSAs that we implemented were of 3 types, basically. When the primary is on, the secondary decides not to transmit at all. And that is the first scheme. And when the primary is on, when we decide to use NC-OFDM to improve spectral utilization, but only for but at the cost of increased leakage into the primary's band. And the third scheme is an interference suppression scheme that we use to suppress this leakage in NC-OFDM further down and better utilize the white space. The primary used in this case was a wireless microphone signal. So this is our experimental system setup. A wireless microphone signal was emulated using a vector signal generator with a bandwidth of 200 kilohertz. And it was sensed, there was a spectrum sensing module co-located with the secondary transmitter. The secondary transmitter is an NC-OFDM transmitter with an advanced interference avoidance scheme. And we also have a monitoring node to observe the spectrum in the same vicinity. So functionally, the protocol of DSA looks like this, with frequency time axis. The secondary user transmits for a fixed duration of time, followed by a quiet period where it measures the local spectrum and decides what subcarriers to use and what kind of scheme to use, whether to use NC-OFDM or normal OFDM. And it keeps repeating till it has finished the practice. Now, the wireless microphone, as I mentioned, occupies the bandwidth of 200 kilohertz. And we refer to the LTE standard to fix our secondary system parameters. And in the LTE, a resource block is defined as a frequency block of width 180 kilohertz. But since a wireless microphone occupies a little more than that, we decided to turn off 3 subcarriers, one adjacent to the primary's band of operation. So the spectrum sensing module is based on an energy detector. It calculates the PSD and also estimates a noise floor based on Samson's technique called Rancoder filtering, and fixes a threshold to determine a spectral mask at the secondary transmitter.
Are you calculating the PSD?
That was yesterday.
So the PSD is so I have the sensing flow graph following.
I'm just asking which PSD algorithm.
We use a period. So the NC-OFDM transceiver looks, the block diagram, simplified block diagram looks like this. We reuse the OFDM modulator, demodulator blocks in GNU radio, and the green blocks show our addition of 2 blocks which control the subcarriers that have to be turned on or turned off. And this subcarrier, as I mentioned earlier, has to be shared between the transmitter as well as the receiver over the common control channel. And this is basically this telling what will be the symbol rate for NC-OFDM based on the number of subcarriers. The occupied tones basically refer to the number of subcarriers turned on in NC-OFDM, and the ADC rate for USRP2 is fixed. So with controlling the decimation, we can fix, and we configure our system to fit for the LTE specification. So here's a spectrogram and a spectrum of NC-OFDM transmission for a typical mask. As you can see, there is some spectral leakage in the notches mentioned there, and in order to suppress these spectral notches as they will interfere with the primary's operation, our collaborators from Japan suggested a technique called interference avoidance using partition frequency and time domain processing. It's a modified NC-OFDM transmitter with the lower chain being added together to introduce something called as carrier cancellation, which the operations are explained in the next few slides. I'll leave this. So the basic scheme here is that the input symbols coming to an NC-OFDM modulator are split in two streams, and they are complementary in nature. That means some of the subcarriers are processed by the lower stream shown before, and some of the subcarriers are processed in the upper stream. In the upper stream, we perform a widely known domain processing by shaping the OFDM symbol with a raised cosine filter, and also adding the tail of the current symbol to the cyclic prefix, shaped cyclic prefix of the next symbol. So this basically provides, as we know, time windowing provides additional side lobe suppression. This provides additional suppression in the center of the notch in 3 resource blocks. It provides more suppression in the center of the notch. To provide more suppression in the edges of the notch, we use frequency domain processing on the lower stream here, which uses the complementary mask of subcarriers. In other words, the lower stream carries only the CC suppressed subcarriers as shown in light blue there, to calculate two carrier cancellation tones, which are specially modulated to suppress the leakage at the edges of the notch. So this split approach ensures the uniform suppression across the notch at the edges due to carrier cancellation, and at the center due to time windowing. And before I move on to the implementation details, quickly mentioning what is the platform that we used. This provides a brief overview of how the GNU Radio USRP2 platform looks. The USRP2 is a readily available, low-cost external hardware with an RF data board. We operated in the 2.4 and 5 gigahertz band, the ISM band, for all our experiments. And GNU Radio comes with, it's an open source radio with C++ and Python blocks, C++ signal processing blocks, and Python application. So here's the flow graph for the GNU Radio. The GNU Radio flow graph for the NC-OFDM module. The first block, called the mapper, is where the subcarriers are used to turn off or turn on certain subcarriers based on subcarrier map is used to turn off or turn on the subcarriers, and followed by the preamble, and it performs the FFT and adds the cyclic prefix and sends it to a sink. A sink here refers to the hardware USRP2 there to drive the ADCs and the RF data board. The modified flow graph for the NC-OFDM IA-PFT scheme, which I just explained, which provides additional suppression, is shown here with the parallel path in the lower stream that calculates the carrier cancellation tones to be added to provide additional suppression. And we performed an experiment where we wanted to compare by PSD of the transmitted spectrum as to how much suppression gain do we achieve. So we had a wireless microphone signal sent by the vector signal generator in the orbit environment, and a secondary sensing and transmitting unit. And we observed the spectrum over the air on a monitoring node. Some of the details of the spectrum sensor and the secondary transmitter are given here. As we said, the LT specification dictates us to use the resource block bandwidth of 180 kilohertz, and we have 12 resource blocks with 12 subcarriers in each resource block, and therefore an occupied number of subcarriers is 144, which leads to a bandwidth of 2.16 megahertz with a 3.84, which is. And we use for secondary transmission, we use QPSK and an FFT size of 256, which is the same as the sensing. So just a quick overview of how the resource blocks are. So the white resource blocks shown here are turned off, and that's where the notch is created. And on the monitoring node, when you plotted the spectrum, as you can see, the blue curve represents the NC-OFDM transmission, and the black is where there is no transmission, and the red curve shows how much suppression. As you can see, It's easily about 10 dB of additional suppression through the use of IA-PFT.
What is this little peak in the middle?
So this peak we believe is due to the local oscillator leakage in the QSRP2, which always persists when we try to tune to that. So we tune to 5 gigahertz and we observe there is a significant local oscillator leakage. That's the reason why we wanted to move the spectral notch towards the left side instead of keeping it in the center. And the spectrogram for our DSA operations can be summarized in these two illustrations, these two figures. The first figure shows when we use only OFDM transmission, the most basic form of dynamic spectrum access, and then we use NC-OFDM with interference avoidance capability called IA-PFT. And you can see that for the entire duration of the wireless microphone, there is a spectral notch created. We also did an experiment where we varied the secondary transmit power and we measured the amount of suppression that we achieved due to this technique. And we found that it remains to be linear for a significant range of secondary transmit powers, except for the higher transmit powers where it saturates the amplifiers. With this setup, we wanted to do some primary-secondary coexistence experiments where we replace the primary system from a wireless microphone to a digital packet transceiver. And we also wanted to verify the performance gain at the primary, which was predicted by the RF suppression gain shown here, which happens to be about 10 dB. So therefore, we plotted the bit error rate at the primary receiver in the presence of both NC-OFDM and IA-PFT transmitter. So the x-axis shows the primary transmit, increasing primary transmit amplitudes, and the y-axis is the bit error rate of the primary. The blue curve is when we measured the primary's bit error rate with the NC-OFDM transmitter on. And the red curve, which is the average of the scatter plot, is the one which we measured in the presence of IA-PFT. And we can see that at say 10 to the minus 3 or 2, it is somewhere about 10 dB of suppression, which was predicted by the RF suppression. We also performed another experiment in which we varied the secondary transmit power, except that we are reducing the power now in the x-axis. And the bit error rate curves for the primary in the presence of NC-OFDM and IA-PFT are shown here. And here also we can see that the performance gain is close to 10 dB from, at 10 to the minus 3. So having this setup ready, we wanted to move on to the development of link rendezvous protocol, which provides us a control channel where we can exchange the spectral masks before assigning or deassigning the subcarriers. So this shows a timing diagram for the link rendezvous protocol where we have two co-located spectrum sensors at the transmitter and receiver, and they exchange the spectral mask to derive a commonly usable white space. And after the allocation is done and we have decided on which subcarriers to use, we go ahead and send that mask to be used at the receiver. For now, we assume that the transmitter and receiver must have the exact same spectral mask to be able to receive the packets correctly. There is no correction scheme as yet in this. With this setting, we wanted to do an experiment where we wanted to see if hidden nodes are being taken into account, and we did an experiment to verify whether the spectral masks were exchanged accurately. And this is a performance curve for secondary when only two links are present and use a complementary subcarrier mask, and we varied the power of one of the links, which we call the interfering link, and wanted to see how the packet success rate drops with increasing transmit power. So to quickly draw some conclusions from this work, we validated through simulations that an AIMD law-based decentralized spectrum allocation scheme is feasible. And then we quickly moved on to the development and implementation of a platform which enables us to perform advanced dynamic spectrum access, which will be required to do a subcarrier assignment later at a later stage. But we also wanted to prove first that it behaves well with the primary system and provides enough suppression, and therefore we introduced the scheme called IA-PFT and verified that performance gain is about 10 dB through RF spectrum, over the air RF spectrum, as well as through the primary performance in terms of bit error. And finally, we designed the link rendezvous protocol and implemented this AIMD law-based spectrum allocation on the new radio platform for single link for now. With more available nodes, I would like to simulate. I would like to do experiments where multiple links would would use the AIMD process to assign subcarriers.
You're fortunate because E1 is going to set it up on orbit, and you can do all these experiments in California in your free time. I got nothing to do in the weekends, so.
Yes. So some.
I thought he just said he was willing to stay out for next year, right?
I think he has a ticket for California already.
So some of the future works is on this work, implementation work is to design what we call as a back-off honk signal required in the all back-off model. In the simulations we saw in an all back-off model that when a link undergoes multiplicative decrease, all the interfering links must undergo multiplicative decrease. In simulations we can ensure that, but in practice to be able to enforce some kind of back off within some duration, we need to introduce something called as a back off honk. All it does is it finds the interfering subcarriers and picks some subset of those subcarriers, and based on the sensed energy on those subcarriers, assigns power for a certain fixed duration in order to drive them into.
So tell us whose idea is this one?
So it was suggested by Professor Ray.
I find in real life, I'd like to have all honking stop. So I think that kind of philosophically.
Cognitive roadways were in India, and it's all based on
Lot of honking.
honking and situational awareness is a good word for it. You listen to all the noises around.
Well, honking is good as long as everybody knows the meaning of honking. Somebody just damaged my car by making a left turn onto oncoming traffic. You know how people sometimes assume that if you really accelerate when it turns green, the other guy's going to be polite and let you through.
Yeah.
Well, maybe the other guy was looking at his smartphone or something, and of course pushing back into me. Maybe honking would have avoided that. I
Were
don't know.
you the?
It was just the passive
You were watching.
waiting behind.
Well, in
Passive
India,
victims.
there are so many unguarded intersections, and there's very disciplined protocol for honking.
There you go. There's a beautiful YouTube with like 5 lanes coming into some kind of crossroad, and somehow everybody harmoniously gets through. No
I
jam.
prefer the intersection place in China where they just keep showing cars and people and bikes, more cars and colliding hundreds. Getting spun around.
But the idea here was to go to one side the control channel is the headache, so if you don't need any current, you can try to do something by implementing a higher power get out of my radio signal, which forces everybody to play.
Right. And the higher power will certainly increase the radius under which the measurement is
So
still
at least
valid.
you don't have a...
Indeed.
But he needed to finish that, but we're letting him
Go become millionaire in California?
That would be nice, but he's joining Marvel, where I don't
Oh,
think that he
I don't know.
Next one. But once
Right.
you're in California, there are like 9 lives, the last of which is at the venture capital. In between, you have all these phases, entrepreneurs.
It's like reincarnation. First is slave,
Overworked
technician,
slave, technician, then
Well, I hope I'm not doing
CDO.
There's actually a 10th phase, which is philanthropist. We expect you to give back to the department. If you are a venture capitalist, you certainly have enough side money to send your way.
We're starting at some not so low level, right? We're getting some not so advanced position.
at Marvel. It's a senior position. But it's since so they said I'm falling short by 1 year of experience. So I don't know what that means. So
You're getting a promotion in 1 year.
that's my.
Remember to ask
I
for
hope,
it.
I hope they remember.
But let's not forget to thank for a very good talk and excellent work.
Thank you.
You should say, like, as your advisor, I feel like but you talk so much with Ivan and Ray, and make sure you say that.
Yeah, so I mean, this wouldn't have been possible at all without, of course, Ray's belief that I can do implementation of research, and of course, Ivan was really helpful with setting up all the platforms so far that we've used, and we've had really tough time getting the platform at a stage that we can use and do these experiments. It took a lot of time for us to work with an open source software and get it working for our requirements. So I really thank.
We went through all the baby steps in radio.
It's impressive. It's hard to do implementation in 1 year.
I think future students now should use this platform to make move
Now it's
forward, because
usable.
the whole idea which I tell people is, okay, God mentioned, why not CSM is fine, but now you have control over the frequency and time and space. You can do anything now.
Sure.
If you want to theoretically, maybe just doing the simple thing is just as good, but you want to try it.
It's impressive, yeah. Otherwise, it would take forever to do implementation if you have to build everything from scratch.
So Ivan also has a new board which is much more powerful, so we are trying to port some of this.
The new software defined range, right? Yeah, I know. Excellent.
Thank you.